Welcome to Linear Equations. I guess you thought, hey, equations, I know something about those, because here are a few here. I've been doing a bit of scribbling, as you can see, and I've got some equations there circled in green, and this comes from a unit on algebra, doesn't it, where we're using letters instead of numbers to solve puzzles. Hey, here's a little puzzle down here. I triple a number, add 17, the answer is 92. What is the number? Hey, you could write a mathematical sentence and try to solve that problem. Here's another one. And mathematical sentences, of course, are also called equations. And what are we doing in an equation? We're equating, or putting two sides equal to each other. And then we're going to try and use that mathematically to solve the puzzle. So you've done a bit of this in the past. The only thing is, we have to look at this word a bit later on, linear. Why are they linear equations? You can see I played around with the scribbles here with lots of other pieces of algebra that aren't equations. Oh, here's another equation down here. I left this one out. There's something that is a formula or an equation, and these other things here are formulas that lead on, special equations, aren't they? They're formulas or rules in science and maths that allow you to find things. So that's what we're doing. We're going to revisit equations and just develop our skills in algebra, where we're just letting a number, a letter stand for a number, or that's what we call a pronumeral. I don't know, how much fun do you want to have here? Here's one down here. This one, I've got a little asterisk there, because this is an interesting sort of everyday practical problem. The boss has $1,000 total to spend on you. It's a bonus for you, but whatever he gives you has to be taxed at 25%, and he doesn't actually want to go over the $1,000, so you can't have all the $1,000. Right? The overall total, what you get and what he has to pay to the tax department, which is 25% of what you get, has to come to $1,000. How much do you get? And the answer is not what you might think, $750. Not $750. So, what is it? Could you use algebra to solve that little everyday sort of practical problem? You could let X be what he's going to give you, and then of course you've got to add tax to it. You might like to pause the presentation now and have a go at solving that little problem using X's, using algebra. It's a good tool. So have a go and see what you think. I'm going to go on now, so come down with me here and let's have a look at what we've decided in the past was a good way of looking at algebra. And perhaps first of all we might have a look at a problem like this in terms of solving equations, and then we'll get on to that bonus problem in a minute. So if you had an equation like this, you're trying to find x. If you go to x, you can see it's been multiplied by 3, and then 2's been added, and the answer is 5. So let's unpack our present here and go backwards. Let's take 2 from both sides, and if we wrote that out in full, we'd have that. If we take 2 from both sides, we'll still maintain the equality. They'll be equal. We're going backwards to what's been done. So that would remove the 2 from that side. So 3x would equal 3. And then if we now divide by 3, then we'll do it over here, 3x over 3, 3 over 3, x equals 1. Now usually, because we've got an equal sign all the way down here, we usually put an implied sign here. That line implies or leads to the next line. So that's not a bad system. If you remember, we've discussed this before. When's your birthday? Your maths teacher's going to give you a present. What sort of present would a maths teacher give you? He or she'll give you X. Okay, so I'm going to give you X for your present now, and I'm going to put it in a box. There you are. So I'm then going to wrap the box up. So I've boxed it, box it. Now I'm going to wrap it. So we'll wrap this present in here now. And then we better put a ribbon on it. Going to ribbon it. So we're going to have ribbon here, and it's looking pretty good at this stage. Do you think you're worth it? Anyway, there we go. So how are you going to get your present out? You're going to go backwards, aren't you? Take off the ribbon. You might want to use it later, and then unwrap it and take it out the box. So it's something what we call is inverse operations. Do the inverse of the opposite. Inverse ops in reverse order. Reverse order here. So we're going to go backwards. And that's exactly what we're doing up here with our operations done on X. We want to undo them. We're going to go backwards and find what that original number was. Let's do a bigger one. Let's do something like 2x take 3 all over 5 is, what can we say? Let's say 10. Okay. Let's do the same thing again. You go to x, you say what's been done to x? It's been multiplied by 2, 3's been taken away, so we're just coming along here. That's our first step. Then 3 was taken away, then it was divided by 5. To get x back again, let's do the reverse steps. Let's multiply this side by 5, and we get 2x take 3, multiply this side by 5, we get 50. So we can put the implied sign there. So we've reversed that. Now let's reverse subtraction by 3. So we will add 3. Do you want to put the steps in? You can put the steps in if you like. 50 plus 3. So this is 2x equals 53. Now what's the last step to do? Let's divide by 2. So do you want to put the steps in? Divide by 2, both sides by 2. So that means the answer is half of this one, 16, oops, hang on, 26.5. Okay, 53 divided by 2. Do you get the hang of it? This box and gift idea, unwrap your present, is not a bad way of thinking about it. Well, I guess you're really waiting to find out about that bonus problem, so let's have a look. Let's look at the solution. Let my amount that I get be X dollars. So therefore, the tax will equal 25% of X, or 0.25x. 25%, remember, percent means per 100. So it's 25 over 100, or 0.25x. Therefore, my amount plus 0.25 of that has to equal $1,000. Now, can we collect these up? That's 1x plus 0.25x. That's 1.25x. Collecting up the x's that we've got now. So that implies that. So now what's been done to x has been times by 1.25. We will now divide both sides by 1.25. Now you could do that on the calculator, or you could call 1.25 1 1/4, or 5 over 4, and without a calculator then, just let's watch it. Dividing by a fraction is multiplying by the reciprocal. So then we could say 5s into 1,000 go 200. So x is 800. I received, always state your answer in the context of the question, I receive $800. And the tax people get 1/4 of that, that's 200, making a total of 1,000. So that was an interesting little problem. Most people say the answer is 750. I hope you can see why it isn't, because you would lose $50. You're paying tax on what you get, not on the 1,000. Okay, so think about that one. Algebra can be useful in solving everyday problems, as well as doing high-powered mathematics for engineering and so on. Let's come down and have a look at some of the things you've seen in the past, and you might have forgotten these. This is a recall for Pearson's, and I'm basing this presentation on screen clippings from Pearson, so have a look at their book there. So this is a general review in Chapter 4 of what's called linear relationships. So there are some things that we expect you might have seen before, and if you are a bit doubtful, you can read that there and go to over here Pearson's worksheets for each particular area. In this first presentation, part 1, we're mainly going to be interested in solving equations. But I thought you might like to do a general recall of all of this to just brush up on what algebra is about. So in this first one, you're substituting t values into this expression and finding out what p is. So the answers are all over here, check it out. In this one, you're unpacking your present like we've just done with the equations there, and plotting points. Do you remember the x number is first on the x-axis there, the y number is second. So you need a little grid type thing just to review that. Then as we go down here, do a Cartesian XY system, substitute these values into each formula there and see if it forms a straight line. It should, shouldn't it? Because a straight line is given by y equals mx plus c, where this is the slope or gradient and this is the y-intercept, where it cuts the y-axis. Are you starting to remember some of these things? Okay, the answers are down the side there. And then 6, 7 and 8 is getting it in the form y equals mx plus c. Some special cases here of straight lines in question 5. See what you think of those. Gradient of the line or slope is y step on x step. Do you remember that one? Which is y2 take y1 over x2 take x1. And then drawing these two and finding where they intersect. Alright, let's come up the top now, and you can pause the presentation too far and see if you can do some of those. So there's question 1 to 4 there, and as we go down we'll just there's the answers to question 4. We just go a little bit further down to D, and you can pause them and just check whether you've got the correct points. Okay, just go up a little bit to question 5 there now, sketching those graphs, and 5, 6, 7 and 8, and the answers to those are down here, of course. Alright, so like you to toggle back and do those problems and check your answers just as a bit of a brush up there. Alright, let's move on. We're looking at, in this presentation, a focus on linear equations. Now, we've been talking about equations. They're expressions where two things are being made equal or equated to each other. Now, you've got an equal sign in there. But what is linear? Well, you can see the word linear. Oh, something to do with a line, and here it is here, Pearson's describing it. You would get a straight line graph. So, for example, if you took a linear equation like this, what it's saying is this expression here in x, if you drew y equals 3x plus 2, it would give a straight line. So therefore this is called a linear equation, because the expression involved in terms of the variable x is going to plot as a straight line. And actually they then start to talk about this independent variable and dependent variable. What we say is, if we are looking at y equals 3x plus 2, we say, well, what we do here is we've got the x-axis and the y-axis. We think of what's on the x-axis as the independent variable, because as we change that, we consider that y is changing in response to that, because it says y equals this dependence on x. Y is 3 times x plus 2. So here we think of, we'll go through it too, and it'll be fairly steep, won't it? So we think of y as dependent upon x. As we change x, y responds to it and is dependent upon it. So that's the dependent variable. So a couple of little names in there for later on. But there we are. That's a linear relationship or a linear equation in y, and here's another version there. So they're all equating, and what we're going to be doing in this unit is talking about linear relationships. So we're only going to be talking about this sort of expression, no squares in it, and so on. And so equations like this will only have one solution. So you might like to read this in Pearson's and just follow it up a bit. Let's go on and have a look at some of these equations. So here's an interesting one. I've just skipped it, so I have to go back now. Here's an interesting one. You might say, well, all these equations and stuff, are they useful? Well, I've picked an example out for you here in chemistry. Now, at this stage, you don't know how much chemistry and balancing of equations you do, but here's a big one. This is a reaction between a silicate and a carbonate here, and it's a big one. It's bigger than what you've been doing. And let's say we don't know how many molecules of these reactants are necessary to balance and to produce the right or balanced number of molecules of the products. Let's say we don't know. How could you use mathematics to work it out? Well, you can look, let A be that, we don't know how many molecules of that, B be that, we don't know how many molecules of these things are going to be involved to produce a balanced equation. But we could make up a set of linear equations in mathematics to solve it. Let's do the calcium atoms. We know that in a chemical reaction like this, matter is neither created nor lost. Okay, so the number of calcium atoms on this side, whatever that comes to, can't disappear. They have to equal the number of calcium atoms on that side. So let's add them up. On the reactant side, we got A plus B. There's A lots of calcium and B lots of calcium. On this side, hey, there's a 2 in there. So there's going to be 2C calcium atoms, and in here 3D calcium atoms. And the two sides must balance out. You can't lose calcium atoms in this type of reaction. It's not a nuclear reaction, mate. Aluminium atoms, how many do we start with? There's 2, but we've got A lots of that. That's 2A. And where do they go? Into this oxide here. So we've got 2 aluminiums in there, and there's D lots of them, so it's 2D. Can you see what we're doing? We're creating little summary equations for each type of atom. And then if we could solve that system, solve this system, now it's bigger than what we're going to do this year. This is getting into year 12 stuff now. But can you see where your work with linear equations might lead? To solving this system and balancing this equation. Well, you might like to check out oxygen atoms and carbon atoms. And I don't know, if you're smart about yourself here, you could actually try to solve this by hand, juggling the equations around and combining them. Now, will we do a bit of that in with 2 equations later on in this course? But that's a bit of a challenge for you. It is possible for you to solve this system by interchanging A's and C's and trying to eliminate all but one variable. I wonder if you can do that. Anyway, here's the answer. There was 1 of that, so A was 1, B was 6, C was 2. Uh-oh, how many of those we got? D was just 1, and C there, E there, sorry, was 6. So I wonder if you'd like to play with that, because that's getting pretty sophisticated, a bit exciting for you, rather than just doing our introductory linear equations. Okay, so if you want to play, pause the presentation and have a go. I'm going to move on now, so come down with me now. Okay, so here we are. We've got our first worked example from Pearson's. Now, I'm dealing with this differently from Pearson's. They put lots of worked examples and then lots of problems. I've split the worked examples away from each of the types of problems. So we're going to do worked example 1 and then the question from Pearson's based on that. Okay, so here we are. 5x take 6 equals 34. We write the equation down, and remember what we're going to do, we're unpacking our present. So x has been times by 5 and 6 has been taken away. To get x back again, we do the reverse operations in reverse order. So we're going to add 6. If we add 6 to both sides, that becomes 5x, and on the other side 34 plus 6 is 40. Then we need to reverse this, divide by 5, x is equal to 8. You can put the working steps in if you wish. 5x over 5 equals 40 over 5. Can put that in if you wish. I prefer to lead on here with implied signs to give some sort of sentence structure. This leads to this leads to this. Notice we don't put an equals in there. We only have one equals in any equation expression that's in the middle. Okay. Now we really should check our answer for later on, because sometimes you get what's called extraneous solutions, and not in these easy ones, but we will check our problem later for the correct solution here. So if we stick x is 8 in here, we get 40 take 6 is 34, which checks out. So you should set that out. I'm doing the left hand side, I'm checking it, putting the number in, and it works. Let's go to the next one there, in looking at unpacking your present again. So a has been, what's next to it? Times by 3. Then what's next? Oh, this is straight underneath, been divided by 2, and then 4's been added. Okay, so what we're going to do now is to do the reverse of that. So we're going to unpack that. We're going to back up here. So we've got to subtract 4. So that implies if you take 4 away, we'll just get 3a on 2. Neg 1 take 4, they don't put that working step in, is neg 5. Okay, now we reverse the division by 2. We will multiply both sides by 2. So if you just checked it with a working step, multiplying that by 2 will equal neg 5 times 2, so you don't have to put that in. Comes to 3a equals neg 10. That implies that. Okay, then we're going to divide by 3, and neg 10 over 3 is neg 3 1/3. Okay. Alright, so you could then check your answer. Notice that we're not expecting any more as we go on and apply mathematics. We're not expecting that the answers will always be whole numbers. In practice, of course, we would expect decimals and all sorts of values, so don't get fazed by that. Stick to your method, unpack your present, and be sure of your steps. Okay, let's write down the left-hand side, and if we stick a in there, 3 times neg 3 1/3, let's do it over here. 3 times neg 3 is neg 9, 3 times 1/3 here is or 3 is negative 30 is neg 1. So here, oh, they've done it this way, so then it is neg 10. So they've done it as changing this to an improper fraction and then cancelling, so that's okay, cancelling like that, or you could do it this way that I've got over here. That's neg 10 over 2 plus 4, checking that you can get that. I suppose you could use a calculator, but you should be able to do some of this checking by hand. Let's go down and do the first question. Well, here's the first question. Now, we'd want to do most of these, certainly every other part, A, C, E, etc. But you must have a high skill level in this stuff. Let's have a look at a couple that look different. I'll make a similar one up over here. 3 take 2n equals, let's say, 10. Can you see the difference? The n term has come second. So n, what would we say? N has been times by neg 2. Remember, the sign to the left of n. belongs to it. The sign to the left of this term belongs to it. Then 3 is really plus 3, so 3 has been added. So to get n back again, we'll do the reverse here. Let's take away the 3. So that implies neg 2n equals 7. And then dividing by neg 2, n will equal neg 7 over 2, which is neg 3.5, if you like. Generally, it's deemed that the simplest form for the answer is a mixed number like that. Okay, so here you can call it neg 7 over 2, or 7 over neg 2, or neg just level with the line. They all mean the same thing. Alright, so watch those which are set up, if you like, backwards, like this, a number and then the pronumeral term. Just be careful with those. Use some sort of system to think about what's been done and how you're going to get x back again. Alright, so pause the presentation now, and as you do each one, toggle forward, because just down the bottom here is, or are the solutions. So you can have a go at those and toggle down each time to check your answer. So you can go back now and have a go at that. Now I'm going to go on. Okay, so here's the next type of example, and in this one we've got a letter on both sides. So let's have a look at this first one. Something like, I thought of a number, I multiplied by 5, subtracted 3, and the answer was the same as doubling the number and adding 6. So you can see where that sort of expression might come from. So here's our first line, and the first thing is to do what they say here, collect up like terms. In other words, you want all the pronumeral terms together on one side. It's called collecting terms that are like each other. Collect like terms in the pronumeral terms. Okay, so what are we going to do? Well, let's subtract 2a from both sides, and then we would have 3a take 3, and subtracting 2a from there, it would disappear and we'd be left with 6. Okay, now you might like to put in the steps there. 5a take 3 take 2a equals 2a plus 6 take 2a. So that's sort of proving that it works. Over here, 3a take 3 equals 6. Okay, so this, you don't have to put this working line in, but that's what's happening there. You're subtracting 2a from both sides. Now, of course, you can use the same process. A has been times by 3, and then 3 was subtracted. Go in reverse, add 3 to both sides, we'll get 3a equals 9. Divide both sides by 3, we'll get a equals 3. Checking in your left-hand side, you get 12. In the right-hand side, you get 12 when you replace a by 3. Therefore, the solution checks. Okay, so don't forget to do that little check at the end. Let's have a look at the second one now. So here, 2a take 5 equals 6a take 1. Okay, now what they've done here, because most people like to work from left to right, they've said, well, let's write this equation the other way around. 6a plus 1 equals 2a take 5. So that when you take away 2a, you get 4a plus 1 equals neg 5. You can do it as it stands. I'll show you what happens here, though. There's two other ways of doing this. If you want to work to the left-hand side, subtract 6a. Now 2a take 5 take 6a equals 6a plus 1 take 6a. So it's going to work, but this is our problem. 2a take 6a is neg 4a. A lot of people don't like to see that negative come up. 6a take 6a is 1. Okay, so can you see the idea of why they've switched it the other side so that you don't end up with a negative? But this will still work. A has been times by neg 4, and then 5's been subtracted, add to 5 is 6, and then divide by neg 4 is 6 over neg 4, or neg 1.5, or neg 3 over 2. So we'll give the same answer as this down here, where you're reversing that, but some people don't like to work with this negative 4a. Well, there's another way of doing it. You could actually start with this as it stands, subtract 2a, move terms to the right. You don't have to always work on the left. So if we subtract 2a, 6a plus 1, take 2a. So neg 5 equals 4a plus 1. Then it's been times by 4. 1's been added. Let's subtract 1. Neg 6 equals 4a. Divide by 4. Neg 6 over 4 equals a. Neg 3 over 2 equals a, or neg 1.5. So, putting those little implied signs in there. What do you want to do? Pearson's is saying work always to the left. I think you should be flexible, should be prepared to collect terms on either side, because an equation you can read either way. Left equals right, or right equals left. Anyway, have a go and see which way you prefer. There are 3 ways. Put the bigger a term on the left so you don't get any negative a terms, or do it as it stands and work to the left, or the third one, keep the a term positive by moving that a across to the right. So there's a few different ways. They'll all give you the same answer. And at the end, checking the left hand side, putting neg 3 over 2 in place of a, it comes to neg 8. Checking the right hand side, putting in, instead of a, neg 3 over 2, and checking that it works. Okay, so that's good. You might pause the presentation and just check that. But let's go down now to the third one. There's brackets. Always remember bread mass, do the brackets first. So expand the brackets. Now we've done some work on that before. So it's, what is it? It's 4 lots of k and 4 lots of 1. Giving that 3 lots of 6, 18, 3 lots of neg k, neg 3k. Now we have got to move some terms around, collect like terms. So this time what will we do? We'll add 3k to both sides. Let's just put that down as a working step over here. 4k plus 4 equals 18, take 3k. Now I want to remove it from this side, so I will add 3k. Watch it work. Why does it remove it? If I add 3k to both sides, it looks like this. And because I've got a negative and I'm adding it, that will disappear. So this will be 7k plus 4 equals 18. Okay, that's how they got this line over here. So just check that. If it's neg 3k and I want to remove that neg 3k, I'll add 3k. And then it's going on as before. K has been times by 7 and 4's been added. So we will do the inverse operations in reverse order if you like. We'll take away 4. We're left with 7k. 18 take 4 is 14. And then dividing by 7. Reversing these 2 steps. K is 2. Checking the answer back in the original equation. If I put k is 2 in there, I get 12. Put k is 2 in there, I also get 12. So the solution checks. Alright, so do the brackets first, always in that sort of situation. Let's go down and try some. So again, you probably need to do alternate parts here, every other part at least, to get your skills up. Watching for the negative ones, like just how would you do that one? Okay, so you have a few choices there about changing the equation around first, working to the left, or just working with it as it is. So I'll leave you to perhaps toggle back and look at some of the solutions and then go on. Now, you'll freeze this, try a part, but always after each part, go and check your answer. So down here, of course, are the answers, so you can toggle down after you've done each problem and have a go. So toggle back now. Well, I'll take you back too far, so let's just come here. Okay, we'll just come back to those problems and you can freeze it there and have a go and then move down. Okay, so let's have a look now at moving on. So toggle back, freeze it, have a go, do those problems and then come on. Alright, so still in equation land, what are we going to do now? Oh, can you see the difference? Look at what they're doing to us here. They're fractions. Okay, just remember we're working in algebra land, so it means letters are standing for numbers. So what that means is we can do with x's and other letters exactly what we do with numbers, including our work with fractions. So what are we going to do here? Well, usually when we're working with fractions we try to clear the fraction, clear the denominator first of all to make it simpler. Clear the bottom line, the denominator. And there are actually two ways of doing this. There's method one. I'm not going to use Pearson's method 2 here. I'm going to refer to it over here in a minute and show you the difference. But at the moment I think their method 1 is the best method, and that's to say, well, let's take this equation and I want to get rid of the fractions. They worry people a bit. So if I multiply both sides by the common denominator, the lowest common denominator is 15. The lowest value they both go into, 5 and 3 is 15. So let's multiply both sides by 15. There they are there, 2 15s, one on each side. Now we can say that cancels into that and goes 5 times. This cancels into this and goes 3 times. Okay, so effectively that's gone up there and that's gone up there. Now, that's a bit corrupt mathematics. It's called cross multiplying. But effectively that's what's always going to happen if these cancel. So we've got there then the brackets. 5 by 2x is 10x, 5 by 1 is 5, 3 by x is 3x, 3 by neg 3 is neg 9. Then we're back to subtracting 3x from both sides. 7x plus 5 equals neg 9. X has been times by 7 and 5's been added. We'll subtract 5. What's that? Neg 9 take 5. Directed number work is neg 14. Okay, and then dividing by 7. So we could put implied signs here. Makes it a little bit better mathematically for later on, where we use that to make a statement of how it leads on. Okay, and then checking the solution. No, just too far there. So just checking the solution, putting neg 2 in place of x in this side, you get neg 1 in place of x in this side, you get neg 1, so solution checks. Alright, what does it look like if you do it slightly differently? And the answer here is you could get them both over a common denominator of 15. So let's have a look now at what that method looks like. So here then it will be 5. Okay, now let's make both denominators the same on both sides. So to do that we have to multiply both sides by left hand side by 5 over 5 and this side by 3 over 3. Let's do that. So this becomes 5 times 2x plus 1. Multiplying top and bottom by the same number is like multiplying by 1, so it doesn't change the meaning of the side. And over here we're going to multiply this side by 3 over 3, which is equivalent to 1. So it's 3 lots of x take 3 over 15. Can you see it's the same idea? Because now if the two denominators are the same, then the two numerators must be equal. So you come to the same working line as this here. I think it's a bit more work, so I think this method over here where you are multiplying by the common denominator and then cancelling is a little bit easier, but the notion is still the same. You must find that common denominator. Alright, let's go down and have a look at another one. And here we have the second one that they've got here. X over 3 take 2 equals x take 1 over 4. So what we're going to try and do is to get that common denominator again. Now there's a little bit of a tricky do in this one. The common denominator, the LCD, the lowest common denominator, here is 3 by 4, or 12. Now if we multiply both sides, be careful now, multiply both sides by it. Okay, so let's do it on this side. That term is multiplied by 12, correct. Don't forget, look out, danger, everything on that side has to be multiplied by 12. And then everything on this side multiplied by 12. So that's the trick here. Don't leave this one out. Both sides are multiplied by 12. That is each term on both sides. Don't forget the neg 2, each term on both sides. So what have we got? 12x over 3, that'll cancel to 4x. Take 24, and that will go into that. 3 times 3x take 1. And then we can expand that. 3x take 3. Then subtracting 3x from both sides to, what have they done here now? 7x. Well, that's interesting. 7x equals, what have we got here? So we've got 3x take 3, and they haven't really shown how to get to that line there. 7x plus 5 equals 9. That's interesting. Because here we've got 3x take 3 and 4x. If we took 3x from both sides, it would be x, wouldn't it? So what have we got there? 7x plus 5 equals 14. Now, can you look at that one and see what you think there? How have they gone from 4x take 24 equals 3x take 3 to 7x plus 5 equals neg 9? I think we've got some problems with that one there, because let's just do it over here. 4x take 24 equals 3x take 3. If we subtract 3x from both sides, we get 1x take 24 equals neg 3, and adding 24 to both sides, neg 3 plus 24 is 21. Okay, so I think something went wrong there with that solution, and yes, I think I've screen clipped incorrectly here. This guy has gone back to the previous example. So that's our solution there. So this was wrongly screen clipped. So x is 21. Let's put it now in x over 3 take 2 equals x take 1 over 4. So the left hand side will equal 21 over 3 take 2, which is 7 take 2 is 5, and the right hand side will equal 21 take 1 over 4, which is 20 over 4, which is 5, and you can put which checks. Yeah, so that screen clipping there is incorrect. So we just check that with this solution over here. Alright, do you get the idea? The most important thing is that each term on both sides must be multiplied by that common denominator. Okay, come down. Let's have a look at another one now. And this is this one here, common denominator of 12. 3, right, there's the first denominator, there's the second one. So if we actually multiply by that, we get here multiplying by 12. What have we got here? Oh no, they're doing it a little bit differently. This is method 2 now. Okay, so we can do that. We're multiplying both sides by 4. well, top and bottom by 4 over 4 here, and getting everything over 12. Okay, that common denominator method. So generally we wouldn't do that. If we were doing this problem, we would multiply everything by 12, so it would be 12x, that would cancel. This would be times by 12, this would be times by 12, and it would cancel, so I'd have 4x, take 24, equals 3x, take 1. So that was that other method we were doing before. So you could actually change all the denominators to 12s by doing that and then coming to that and getting that answer. Okay, well, choose your method. I think this method, multiplying each term by the lowest common denominator, is a little bit easier overall to use. Coming down, let's have a look at doing some. So remember the steps. Number 1, find the lowest common denominator, something they both go into, and it's usually the product of the two denominators, unless you can find a smaller number. Okay, find the LCD. Multiply each term on each side by that. On each side by the lowest common denominator. And then we're going to cancel out and simplify. And then what we're going to do, of course, is usual procedure to solve the equation. So we're going to collect up like terms, list down what's been done, unpack your present, do it in reverse order, and that sort of thing. So you need to at least do every other part here. You need to get some practice here, because there's some biggies, things like this in there. Watch out for this one. Don't forget to multiply the 2 by the denominator 3 there. There's only one denominator. But remember, the idea is to clear the denominators first. Clear the denominators. If there's only one of them, then you'll multiply 3 by it. Clear the denominators. Okay, so we don't have to work with fractions around x. Let's get rid of those first. Alright, have a go and see what you think. You need to combine all your skills now, because they're building up here quite a bit. You're getting pronumerals on both sides as well as fractions. Alright, we'll pause presentation, have a go, and toggle down and look at the solutions, because they're just down below here. Okay, so toggle back, have a go, and then we'll move on. Okay, what's the next type of problem? Well, we've done this before, and you saw this back at the introductory screen back there, where we're using a pronumeral to stand for a missing value, and it's puzzle time. Problem solving, or puzzle solving if you like, where you have to introduce your own symbol for something unknown, like the bonus problem if you like. So here we are. The sum of 3 consecutive numbers is 21. What is the number? What are the numbers? So let the first number be x. Consecutive. Do you know what that means? Consecutive means one after the other. Follow each other. No gaps. Follow each other. So the next one will be x plus 1. The next one will be x plus 2. Now the sum of them means you add the 3 numbers up, and the sum is 21. Collecting up all the x's, you got 3x plus 3 equals 21. X has been times by 3, 3's been added, do the reverse. Subtract 3, you'll get 3x on this side, 18 on this, divide by 3, x is 6. So the numbers are 6, 7 and 8. And you should go back and check that that solution works in your original unchanged equation. So this is a bit of fun, using algebra and X's to solve puzzles, often done in problem solving in the real world, and in areas not just like engineering, but economics and so on. Alright, so let's come down, and can you write some equations or mathematical sentences to describe this? I think the key point is you must state what you're doing. Let what? X be the number or whatever. Let X be the number. You could let N. You don't have to use X. And you must start off with that. And then you should state the answer as not X equals, but therefore the number was whatever. So you go into X land, or algebra land, to actually solve the problem, but that's your introduction. You should state the answer in the context. If they ask for the missing number, let X be the number, sure, but then at the end state your number was. Okay, so pause the presentation, do all of these. I think there's only 6 of them, and check your answers as you go. So the answers are down below. Make sure you can prove those. So toggle back, have a go, and check your answers along the way. I'm going to go on now. Okay, so here are some more problems from Pearson's. Nothing new here now. What you are aiming to do here is to solve that equation and just pick out which of these is the correct solution. So you just do the normal thing in solving these equations and then picking out the solution. And I want you to try and solve the equation. Don't check the solutions by substitution in, because that's very it's a very long way, and you are better than that. You can actually solve it and find which of those answers are the right way, rather than just substituting them in. All right. Check those out. I think you should do all of them. There's only 6 equations there, and come down and check your solutions as before. So they are the correct solutions. So toggle back, finish them off, and then we'll go on. Okay, so in Pearson's now, as you know, there are levels. So now we're stepping up to another level. So these are puzzles. So your level of understanding here, does it extend to being able to introduce a pronumeral and then put the words of the problem into a mathematical sentence? So underline the important facts given to you in the problem. What's an example? You want 4 consecutive numbers. Comes to 38, the sum. Okay. Here, this problem, a bit harder. He gave himself twice as many as he gave Nikki, and Min received 3 times as many as Nikki. So it's very important to unravel the important facts and underline them in the problem, I think. So I'll just cross all that out now, and you can do it yourself, like that. But that's an important strategy to make sure you have picked up on all the given information. So that's important for maths later on. Use all the given info. Don't just try and jump in and try and do the problem without reading all aspects of it carefully. Okay, so have a go at those. We'll toggle down for the solutions in a minute. Then there's 11, 12, 13, 14, 15, up to 17 there. I think that's the last one there, 17. Alright, so you can toggle back and look at the first few and freeze it, and then the solutions are down the bottom. Okay, so you might have a go at those. So toggle back as you do a problem, check the solution, go forward and back to make sure you're on the right track. Let's go on to the final bit now, which is the open-ended questions here. Okay, so write 3 different equations, each having a solution of -2, where at least 3 mathematical processes are used. Well, 3 processes, something like 3x plus 2 over 4 equals something. So 3 processes. 1 being times by 3, 2's been added, being divided by 4. So that's what they're talking about. Not just very simple ones, but at least 3 processes and 3 different ones. You might like to use this. What would, if this had a solution of neg 2 for x, what would that equation be? And write some more like that. Okay, well these don't have specific answers because there's lots of different equations that you can write. So they're open-ended. So I'll just show you down below the solutions that they've got, typical solutions, sample answers. So there are some sample answers for that, if you like. They've made some fairly complicated ones with x's on both sides, but you can do the one I did, having all the operations on one side. Alright, well, toggle back and have a go. I hope you've enjoyed that. You're doing well coming along there with those skills. Just check and go back over and make sure you understand what you're doing, because we're going to develop this further in linear relationships, drawing graphs and stuff and so on. So I hope you're enjoying yourself. Your skills are coming along well. I'll catch you in the next presentation.